Thank you for sticking around. So this will be the third lecture in my series on computational geometry with bounded workspace. And so since now the first two times I introduced the model and I showed some basic algorithms yesterday, which got increasingly more sophisticated. Then today I wanted to show one or two more algorithms which have some new tricks which we haven't seen before. And so I didn't coordinate with Dave, but so it fits very well. I will also start speaking about time-space trade-off. So, but for some reason I'm used to saying time-space trade-off instead of space-time trade-off.
That's wrong.
It's I don't know. It's yeah. Maybe it's psychological. But so these time-space trade-offs, they feel a bit different because they're in a smaller regime. So it's not something like n to the d versus n, but n versus log n. So even something more exponential. Okay. So, but let's see how far we get, and let me start with another algorithmic problem that I want to solve. And so this is one of the most basic ones. And so in the usual model, this problem is even so easy that you don't really think about it anymore. And so the problem is the following. So you want to find paths in trees. And what does it mean to find a path in trees? So what is the input? So we have some tree T. So it's a graph and it's a tree. And we have some nodes S and T in the tree. And we want to find a path between these nodes, or the path between these nodes, because we know in the tree there's only one. So find path from S to T. So like this. So here's some tree. And so for example, so this might be S, this might be T. And then what I want is I want to have this sequence of nodes that you have to traverse in order to get from S to T in order. And of course, in the usual model, you would just use something like breadth first search or depth first search, and then you would discover T. And if you set the pointers, so you would start with your search from S, and then if you put your pointers correctly, then you will, as soon as you encounter T, have also no trouble in reconstructing the path from S to T. But of course, this does not work in our model because for breadth first or depth first search, you need to maintain a queue or a stack, and you cannot afford to. So if the tree branches out, you cannot really afford to maintain this structure. So we have to come up with something else. And but so before we can talk about the algorithm, so we also need to think about a little bit how the tree is represented. So maybe let me say a few words. So what exactly does it mean that the input is a tree? So how is T represented? And so this is a bit more important than usual because so we have this assumption that we cannot change the input. So the format or the structure of the input is quite important. So different structures might be to different algorithms. Whereas in the usual model, if you don't like the encoding of your input, you can change it if it's convenient for you, and then use something more efficient. But so here we need to really think about how the tree is represented. And so, but the usual way is of course, so I'm choosing the adjacency list representation. And so adjacency list just means that for every node, so I mean the input is stored in some array, but so this array it contains, so for every node we have the sequence of all the neighbors in some order, right? So for every node, so we store the sequence of neighbors. But there's something that I need. So for my algorithm to be efficient, I also want that there's cross pointers. So between that correspond to the edges, right? So so maybe a usual adjacency. So if you have something like this, you would store it like this. So this is A, B. So let me call these nodes A, B, C, D, E, for example. Then you would store F. Then you will store A has the neighbors. B, C, D, F, E, for example, and B has the neighbors A and C, right? So that would be the usual adjacency list. But I also want to have some cross pointers. So I want that. So, for example, so there's an edge between A and B, and this edge should also be represented by some pointers, such that if I know here B is the neighbor of A, then together with this information that B is the neighbor of A, it also gives me some pointer into the position of the list of B where A is stored, so that somehow I can go back and forth. And so this will be useful for my algorithms later on. So so that I don't have to, if I have B, I don't have to scan the list for A again. And so plus cross pointers. Okay. Good, but that's the way the input is represented. But so, as I said, so this is a bit more important in our model than in the usual model because we cannot really change this representation if we like. Okay, and by now, I think that you have seen quite a few of these algorithms. So you, maybe you're already in the mindset of how you work in this model. And so I think there's a simple algorithm that everybody, so with what we've seen so far, everybody should be able to find some answer to this problem. And so I would claim that what is easy, so the easy thing to do, or maybe by now obvious, I don't know, you can do O of n squared time in O of 1 space. And so why is this easy? So I said you cannot really, so you want to do depth first search, but you cannot really do it because you cannot store the stack. But what you can do is you can just repeat a lot of stuff, right? And so what is the easy thing? So you just start at S, and then we use this adjacency list representation to systematically explore the tree, right? So we start at S. So here is S, and then we have several subtrees starting from which branch out of S. And then what I do is I search. So I just go into every subtree, and I can use this adjacency list representation to systematically traverse this subtree, and to visit all the nodes. So I mean, I can go and I can visit the whole subtree in time which is proportional to the number of nodes in the subtree. So this is where I use this assumption of the cross pointers. So I can just look at all the subtrees and find out which subtree contains T. So exactly one of those subtrees will have to contain T. And so once I found the subtree, I know what is the next step along my path, right? So here I have S, and so I found out that T is in this subtree. So I know I will, so let's say this node here is A. So I know my next step will be A. And then again from A, there are some subtrees hanging off. And then the next thing that I do is again starting from A. So somehow this here now becomes compressed into one subtree. So now I'm at A. And from A I have some subtrees which hang off, right? So maybe like this. And then I explore all the subtrees systematically, right? And I know one of them contains T, and then I know which step I have to take, and so on, right? Everybody understands? Yes, yeah, question?
Excuse me, I want to know, do you store the adjacency list and why the state is not depend on the development?
Well, so it's a tree. So the space is O of n. Right, if the tree has n vertices, it depends on the space is O of n because you have n edges in the tree. Right, but so in general, if you store adjacency lists, then the space would depend on the number of nodes plus the number of edges. But because I'm thinking of a tree, the input size would be proportional to the number of nodes. So it's O of n. But where n is the number of nodes. But so if it's some general graph, if it was some general graph, and I would store the adjacency list, then the space would depend on the number of nodes plus edges. But so this, I think it's common, right? So if you have a graph, it's the input size. Yes.
But you can have a node with a degree as most n minus 1.
Yes, that's right. But yes, so I mean, but the degree is at most n, and you know that the sum of the degrees will be linear. The sum of the degrees will be 2n. Yes, 2n minus 2. Yes?
Can you please write down the pseudocode? I don't quite understand how it works.
The pseudocode for this one?
Yeah.
Okay, yes, let's see. Let's see, I don't have it. Let's see if I can come up with some reasonable pseudocode. So I think what you need is so you have some current node. And so initially this current node will be S. Right? And then the high-level algorithm, it works like this. So for all neighbors of S, okay, or maybe like this. While current node is not T, do. So now, okay, so I abbreviated current node to car. And so while this current node is not T, so T is my target, I'm doing the following for all neighbors of T, of current node. So I can go through the adjacency list and I look at all the neighbors in the adjacency list of T. I do the following, do if contains T, neighbor, or maybe like this. I call some subroutine which I call contain, and so this which I call contains, and so this subroutine is supposed to check whether this subtree rooted at this neighbor contains the node T. And I also need to give it current, so I know what the root is, car. So if it contains, if this subtree contains the neighbor, contains T, the subtree rooted at the neighbor, then so I return true, otherwise I return false. And if this is like this, if this is the case, then I set current to be this neighbor, and I break the for loop. So I'm sorry, this pseudocode is not very nice. And so then here I output current. So this is the high-level algorithm. Is that somehow clear? So, yeah, one question?
Sorry to check whether a subtree contains, from my observation, you are going to call contain recursively on the subtrees.
So I haven't told you yet how contains work. I didn't say how it works yet.
Yes.
So this is a subtree, and I will explain it in 1 minute. Yes. Okay, but so this is the high-level idea. So everybody understands the high-level idea? Yes? And now I need to check now I need to see how contains works. And so let's see. So how did this work? So maybe let me draw a picture how this works. So you have this node current, and you go down to this node neighbor. And you have the adjacency list. So you remember this edge here. And now the tree, it looks like this. So here's some tree. And the idea is that I want to walk along this tree in this manner. So I know basically, so this is my distinguished node. I started here, and I know this edge. So I'm coming through this edge. And so I have a pointer in the adjacency list onto current. And now I take the successor of this edge. I go like this, right? And then I'm at this node. And then I take the successor of this edge in the adjacency list. I go like this. I take the successor. I go like this. There is no successor. I go back. Then I go back. I go back. I go back. I go like this, 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 this. Then I'm back at neighbor. I take the next edge. I repeat like this, like this, like this, like this, like this, like this, this, like this, this. Until I see this edge again through which I entered, right? And then I stop, right? Do you somehow understand what's happening, or?
I do understand what's happening, but I think I'm having difficulty understanding the cross pointer.
Yeah. So the idea of the cross pointer, I think it's more a question of efficiency. So the idea of the cross pointer is when you go from here to here, right? So you know you go, so let me call this A, and this is B. So you go from A to B. Then when you go from A to B, so you that means in your adjacency list you're at node A, and now you know B, right? So this is what it says in the adjacency list here. Here's A, and then the neighbor is B. And so this is some pointer into your input to the node B. But the pointer, it points actually to not only to the node B, but to this A here. And the reason it points to this A here is that that now you know you actually have this edge here, right? And then you can just look. So here you're at A, and then you can see what is the next edge after A, right? So it means that you can immediately go here. Of course, you don't really need those cross pointers, so you could also just remember that you came from A, and then but then you would have to scan through the whole list, right? So somehow what I'm saying is that I can do this here in O of 1 time, right? So this arrow here, I claim that I can, so the cross pointers let me implement this arrow here in constant time, right? Because when I follow this edge, I will be able to know this A, and then I can just look at the next element in the list. If I don't have this, then I would have to scan through the whole list until I find A and the successor of A in the list. And so it might take a long time. Yes, do you understand? And so the reason why this is important is because so I need to where I come from, so this is also some kind of state. So I need to make sure that I don't get into a loop, right? So that I make progress all the time. And so I need to make sure that I advance through these lists. And so this I get because I remember where I'm coming from. And so these lists, they impose some order. And so when I know where I come from, I know I need to take the next edge, right? So when I'm at this node, I just don't know. It's not the only thing that I know that I'm at this node. But when I'm at this node, I know I'm at this node. And I come from, for example, from that node, right? So I'm at B, but I know more than being that I'm just at B, but I know that I'm at B and I came from A. And so this means the next step is I need to go to C, right? And so this helps me to remember when I reach a node how I need to continue, right? And when to stop. Yes? Is that clear? And so, and in particular, I need to remember this edge here, because as soon as I reach this edge, which I through which I entered the subtree for the second time, I know I'm done with the subtree, right? So I need to remember this so that I know when my search can stop. Right? So it's not enough to stop when I see A for the second time, because that would not be enough. I need to stop when I see this edge here for the second time. Yes? Another question?
Don't you keep the successor of each node in the subtree?
What do you mean the successor? So I cannot, remember I only have constant space. So I cannot really store, so the only thing that I can store really, so what my memory contains.
Yeah, I know, but it seems that you keep the successor of each node when you get back, or if you don't do so, then you wouldn't know that you should proceed and not check the node that you had already.
No, because when I go there, I know where I come from, right? So this is the point, that I remember so I do not store it with the node. But the successor I can find because I know where I come from. Right, so it's so when I visit A for the first time, and I take this edge, I don't need to remember that when I leave A that I took this edge, because when I come back to A, I will know that I took this edge because this is the edge through which I come back, right? Because it's a tree. Yes? Is that your question? Yeah? Do you believe that? So I'm sorry. I mean, I could write down pseudocode for this, but it gets a bit messy, so maybe I can do it after. So if you want to see it, I can show it to you afterwards. Because on the board it's probably a bit annoying, but I have it in the paper. Yes?
And in how much memory can this be stored in our read-only memory?
Again?
How much memory does it take to store this information in our read-only memory?
Well, it's linear, right? So for every node, you store just the list of the neighbors and the pointer. Yes. And the pointer is, so remember my assumption was that I can store log n bits. So in total I have O of n words, right? So if I have n nodes in my tree, I need to have O of n words to represent the input. And then a pointer is just an index in the array, so it's again log of n bits. So I think you can, so if I zoom in on this, so this would be b, and this would be some number, and this number would be a pointer to this thing here, and this pointer is just an index to the array. So it's also again log of n bits. It's just some index in the input array. Yes? Okay. Any more questions about this? So, okay, so this is the simple algorithm. But it's so the questions, they are very, very good because it's important to think of what exactly you can do in this model, and it takes some time until you have the feeling of how the input is represented and what you're allowed to do and what you're not allowed to do and what the state is. So it puts you into some different mindset, right? And okay, and so now I claimed this takes O of n squared time, and why does it take O of n squared time? So with this assumption that we have these cross pointers, you can do it in, so you can implement this picture that I drew here in O of n time, right? So one step takes O of n time because so you have to look through subtrees, but the total size of the subtrees is O of n, and then each subtree you take 2n steps. So this is called an Euler tour, what we do of the tree. So this takes about 2n steps. But each step takes a constant time because we just need to somehow maintain pointers in the adjacency lists. We don't have to scan through the list, but we just follow the pointers in a way. And so each step takes linear time, and the path between S and T, it can have length at most n because it's a tree, so the path has at most length, well, actually it's n minus 1 steps. So the total time is O of n squared. Yes? Good. And so from what we've seen so far, you might be satisfied with this, right? So you've seen O of n time, O of n squared time, O of one space, so that somehow comes naturally, right? So we saw that this is what you get for convex highest, this is what we get for triangulations, for Delaunay triangulations. We don't know how to do it for EMSTs, but somehow this seems to be the pattern that emerges, that if you want to have constant space, then you have to pay for it with some significant increase in the running time, so O of n squared instead of n log n or something like this. Yes? Okay, so you think that's it, but it's not. So actually this algorithm is far from optimal. You can do much, much better. And so this is one of the tricks. So this is one of the tricks, a good thing that to know. And when I saw it for the first time, I found it a bit surprising. So I don't know if you will find it surprising. So the question now is, can we do better than this? So can we do better? And indeed we can. And what is the idea? So the idea is use parallelism. And so at first sight it might be surprising, but actually it turns out that somehow parallelism and bounded space, they go together quite well. And somehow this parallel mindset, it helps you to improve a lot of algorithms and to come up with some nice ideas. So let's see a simple idea. So how parallelism can help us. So what exactly do I mean by this? So what does parallelism help in finding a better algorithm? So let's see. So let me explain the idea. So suppose. So we want to do the general same strategy, right? So the strategy that we have for our algorithm is the same. So we want to generate the nodes of the path one by one. And the idea is we're always at some node and we want to find what is the next step that we have to do. So we're in this general situation. So it looks like this. So there's some edge E. And we know this edge E belongs to our path. So we took a step along the path, and here is some node A. So we know in the current situation, we know we entered some node A through an edge E, and we know this edge E belongs to the path. And then we know A has some other neighbors other than this edge E, and this can be many. This can be, as was said, up to n minus 1. So you know there can be many, and we know that one of those trees here contains T. So one of those neighbors will take us to T, but we don't know which one. Yes? So this is what we know. And we need to find out which of these trees contains T. Yes? So as before. So this is the situation we're in. So suppose we enter a node A through an edge E, and so what we need to do is we need to find next step to we need to find the next step to T. Yes? And so the first observation is so that the algorithm that I explained to you last time, it's a bit inefficient. I mean, so there's some obvious inefficiency in the algorithm because, so I said, as soon as I step to A, I completely forgot where I came from and I look at all the neighbors. But of course, it's clear we don't need to look at this one, right? So we know we came through this edge E and we're looking for T. We don't know T. We know for sure that T cannot be where we came from, right? Otherwise, we wouldn't have taken this step. So we don't need to look here. So that's one obvious inefficiency in the algorithm that I explained just 5 minutes ago. But of course, you will notice that this observation doesn't really buy you anything for the algorithm I described. So it doesn't make it better, because it may still be that you need quadratic time, even though you ignore the even if you take into account the fact that the step you made can take you to T, right? But it is a good observation that to make. So we know of one. So do not look into subtree at E, right? So we can ignore this one. But still, so this does not really help us, right? So this doesn't make the algorithm asymptotically faster. So we need to find another trick. And so what is the second trick? And the second trick is the parallelism. And so the trick is now, so as the old algorithm, it would just first go into this tree, look through this tree, and then would go into this tree, look at this, and if it doesn't find T, it goes to the next tree. Then it goes to this tree, searches through this tree, it doesn't find T, it goes to the next tree. Then it goes into this tree, searches this tree, and it finds T, stops, and it goes into this, follows this edge. But this may be bad. And now the idea is we don't search one tree, but we search two trees at the same time. So instead of going into one tree, we have two, so you can think of it as somebody walking along a tree. And so now we don't have just one person walking along a tree, but we take two trees at the same time. So this one and this one. So in a way, so our algorithm splits into two, and one person walks through this tree, the other person walks through this tree. Yes? And we can do this in parallel because we know that this and this search, it just takes constant time. And so if I do it twice in parallel, then again I still need only constant time, and the state is very limited, so I can just move this guy for one step, then I move that guy for one step, then I move this guy for one step, I move that guy for one step, simultaneously. Right? And, yes?
It even works just in case of the balance tree,
no, okay. So you have a good question. So the question is, so what do you do when one of those guys finishes and the other one does not? So what do you do if one of those guys finishes and the other one does not? I mean,
they have a shared flag that then if the person finds the T, then the flag comes to 1 and then to finish. But if the tree is not fully balanced, then the person may take O n times, and then the other one have already finished.
yes.
But in this case, the parallelism don't really work.
Yes. So this is a good point. So now the thing is, what are the stopping conditions? So we all understand that somehow we want to have these two people walking at the same time, but how exactly, what are the stopping conditions? So the first thing is, so as soon as one of those people stop, so as soon as one of these people is done with one tree, it just goes to the next tree. Right? So it may be that this tree is very small. So what else do I need to store? So I store here the next edge which is not explored yet. So I'm going to go through all the neighbors systematically in order, one after the other, right? And I will, and I know that my current state. So in my memory, I will store that I'm looking at A, and I will say what are the neighbors. So what is the current neighbor of A that I want to explore? And so I will have a pointer to the next one. And so as soon as one of the guys is finished, it will just go to the next unexplored tree. Right? And so it may be the case that, for example, here the red guy is stuck in a very large tree, and there are several small trees. So it may be that the green guy goes way ahead of the red guy. But still, as soon as the red guy finishes, it goes into the next unexplored tree. Right? So we have some pointer into the next unexplored tree. As soon as one of the guys finishes in one of the trees, it just goes to the next unexplored trees and continues there. Right? Yes? That's the first thing, right? So, so the first thing is we have a pointer to the next unexplored tree. As soon as some guy finishes in one tree unsuccessfully, it goes to the next tree. Then the second thing is, what do we do if we find T? Of course, if one of the guys finds T, the guy just, so the algorithm just stops. We say we found T and we make the next step. We're done. Okay? So this is the second situation. And there's a third case. The third case is, well, I mean, it belongs to the first case. So what if there's no unexplored tree left? So what happens if, so one of the guys finishes, the other guy is still busy, and one of the guys finishes, tries to go to the next unexplored tree, but there are no more unexplored trees. Right? Then we know where T has to be, right? We know T has to be in the last tree. Even though we haven't found T yet, it has to be in the last tree. Because we looked at all the other trees, we didn't found T yet, we haven't found T yet. We know T has to be somewhere, so it has to be in the tree where we are not yet. Where we're still, the tree we're still working on, but still we can conclude T has to be there. Yes? And this is somehow, this last part is what makes the algorithm efficient. So you don't really, so if T is in a very large tree, so it may be that, so what makes the first algorithm inefficient is that it may be that T is in some very large tree, and all the other trees are very small. And then with the first algorithm, if I really want to find T, I have to look for a long time until I have found T. But actually, I do not have to look all this time until I have found T. It's just enough to know that T is not in the other trees. Right? And so this I can do by this parallelism, that I have two guys searching. So if one guy is stuck in a very large tree which contains T, then I just go, then the other guy will quickly go through the small trees and know that T is not in the small trees, and so we can conclude that it is in a large tree, and even without finding it. Yes, and so this is the main insight where the efficiency comes from. Yes, so this is This is the algorithm, so do you understand, or should I write down some more? Or do you have any questions, or is it clear? I mean, so, but this idea that you do two things at once, so this is very, very useful. Yes? Is there other questions?
The first processor doesn't really work in the third case, that case that no subtree remains and one processor gets stuck in a huge tree.
Yes.
And then the one processor remains busy and then the other is really weak.
No, the other one is also stopped.
Stop.
Okay, so I mean the situation is this.
It's not a good kind of parallelism. Because,
Well, I mean the thing is it's not really, so the parallelism is just in our head. So it's not really, so my computer is not parallel. My computer is sequential. So when I say parallel, I mean I do one step here, one step there, one step here, one step there, one step here, one step there, done, go here. One step here, one step there, one step here, one step there, done, go here. One step here, one step there, one step here, one step there, done, no new tree, stop. Right? So we alternate. So it's not really, it doesn't mean that we do things at the same time, but we somehow think of things happening independently. But the parallelism is sequential, right? So it just means we interleave the steps. And so there's some central control which stops the algorithm at some point. And then we found the next step. Yes? Mm-hmm. And so now let us analyze this. So everybody has some idea of how it works. Or should I write down more? Oh, I didn't write down anything. So maybe I should write down a little bit. So what we want to do is, so let me summarize. We simultaneously search two subtrees taking alternating steps. Right? So we simultaneously search two subtrees and we take alternating steps. So one step in one tree, one step in the other. And so as soon as if we find T, we stop. So if we find T in one subtree, we stop and take the next step and go to neighbor. And then, if do not find T, if we do not find T, then we go to the next unexplored tree. Go to next unexplored tree. And the third situation is, so there's no unexplored trees left, then we just go into the remaining tree, right? So if no unexplored tree is left, stop, go to remaining tree. Yes? Okay? Yes?
If we can go back from T to S, we have the passive reverse.
So what is? So your question is, so I said, so that was the first observation, that you cannot step. So you remember where you came from and you will never take this tree, right? So you only consider the other trees which you have. So you know where you came from, and so this tree you exclude, right? So you cannot go back to S. It cannot happen that you somehow explore some stuff multiple times. Is that your question? Okay, yeah, maybe we can talk about it afterwards, yeah?
Based on the way we explore the subtree
Yeah.
to find where T is located,
Yes.
is it possible we reverse the path because in each step we know where we come from?
No,
We
you.
reverse
The thing is, so remember that we only have constant space, so we only remember one step back, but we cannot remember more. So we don't have this whole stack which tells us where we came from. We just know the last edge where we came from, right? So when I'm here in A, I know that I came through E. I can remember this, but I don't know what happened before. I cannot remember this. This might be too much information to store.
then how we can remember
Um,
for intermediate edges to explore the subtree in contains module?
Yeah, so that was these pictures that I drew. So you use these cross pointers. So you have the edges in sorted order in some order in the adjacency list. And when you enter some edge, you take the next edge, right? So so this information is somehow encoded in where you come from, right? And then you take the next edge. And so this means you will make progress, right? And then at some point, you will just go back. And then you reach the root again, and then you remember the first edge. So you know exactly where you started. And as soon as you go back where you started the whole search, this contained search, then you stop, right? So it's important to know where you came from, and then you have the adjacency list. You can find the next neighbor. And so this ensures that you always make progress, because you always go into some subtree, you explore the subtree, you come back, and then you go to the next subtree. And so you do this by advancing through the adjacency list. And so this means that you never look into the same subtree twice. Yes?
Then the adjacency list must be traversed more than once to find where you have them.
Well, so we have these cross pointers, so you know where you go in, and then you can go to the next one. But if you don't have the cross pointers, you might have to go through the adjacency list all the time, and the running time might blow up. Yes? Yes?
If you don't repeat and check the nodes when you go back from T to S, you can output the path you take when you first time find T.
Exactly. Yeah. No. So you output the nodes whenever you step. So I take this step to A, I output A. I take this step, I output it. And once I'm at T, I don't know exactly what the path is anymore. I just output it along the way into my write-only memory. Yes. So maybe we can talk about it afterwards. Then let me analyze this algorithm. So now we talked about this algorithm, but so how good is it? So what do you think? How much time does it need? So what's the analysis? How long does it take?
It takes as long as
N log n, n? Linear. Yes, so the answer is O of n. So why does the algorithm, so the analysis is, it takes O of n time. And why does it take linear time? And so for this, we need to do some charging argument. And so the charging argument is, so we do a charging argument. And the charging argument, it works as follows. So you're at some current node A. And so you're in this situation where you explore all these subtrees. And the observation is, because I never go back, so I remember where I came from and I never go back, then I know, so as soon as I found the subtree where I have T and I took this step, then I will never again visit any node in one of these other subtrees, right? So as soon as I stepped into this tree, I will never again visit any nodes in these trees, right? Because I cut it off, right? So I know where I came from, I will never go back. So as soon as I am here, I will never go there again, right? You believe this? Yes? And so the observation is, so we take one step in the path. We will never again see nodes in other trees, in other subtrees. Okay. And so now I can charge my work to these nodes in these trees I do not look at any longer. And so what I do is, the observation is that since I have two guys walking simultaneously, it means that for every step I take in the tree for t, right? So the only nodes I will see again, I will walk over multiple times are nodes in the tree for t, but for every step I take in t, in this tree I have taken at least one step in one of those other trees, right? Because I do it simultaneously. And so this means that every step I take here is paid for by a step I take there, right? And so every time I touch a node here, I have touched a node there. And every time I touch a node here, I would have touched a node there for the last time, right? And since every node can be touched only once for the last time, and since there are only n nodes in the tree, the total running time will be O of n. Yes? Yes? So, for every step in T's subtree, we take a step in another subtree, and so this is O of n steps total. Yes? And that's it. Right? And so this means this problem can be solved in linear time and constant space. Yes? And this is surprising, because it says that the standard algorithm you learn for this problem, it's, for finding the shortest path or finding a path in a tree, it's very inefficient. It uses way too much memory. You can do much better. Right? So you don't need all this memory. So for this problem, you can just solve in linear time, so as fast as you can hope for, with basically no memory. You just need a few pointers in the tree, and you just need to jump along the adjacency lists, and then you can solve this problem in linear time, without much more. So this is quite surprising, I find. Maybe you don't, but at least I do. So this is quite an interesting thing, and so the whole improvement came from this trick that you use parallelism instead of doing one thing. So you come up with something stupid, but you do this stupid thing twice, and then you see that there's some redundancies in the tree, and you can through the parallelism you can get rid of these redundancies, right? You won't get stuck in some inefficient computation because you can cut off other alternatives quickly, right? That's quite nice. Good. Yes? Any questions so far? No? Okay. Then, so I'm not sure if I can get to the time-space trade-offs because it took a bit longer than expected. And so there's only maybe 15 minutes or a bit less. So maybe just let me quickly explain one application of this thing. And so because this is not really a geometric problem that I solved here, it's just a very basic graph problem. But so let's see how we can apply this. So let's see one application. And the application that I'm going to show you is how to find shortest path in polygons. Shortest path in polygons. And so let me remind you what this means. So here you have some polygons. So Jason has shown many polygons already. And now let me also draw one. So this is a stylized, complicated polygon, right? And so we are solving the most basic problem, or one of the most basic problems. So what you want to do is, so you have some node S, and you have some node T, and you want to find the shortest path from S to T. And so this means you want to find which connects S to T and which lies completely inside the polygon, right? And as you know, so the idea is, so how do you imagine the shortest path? So this shortest path you can imagine as some kind of a rubber band, right? So here there's one person at S and there's one person at T, and they both have a rope, like so maybe they are connected by a rope like this. which is inside the polygon, and then they start pulling until they cannot pull it anymore, right? And then you can somehow expect that it will look like this. Maybe, and this will be the shortest path, right? So the shortest path in the polygon is a polygonal chain which starts at S, ends at T, and in between it uses edges from S between vertices of the polygon. And all the edges, they are reflex, so this means the internal angle here. So since all the vertices of the shortest path are also vertices of the polygon, except for S and T maybe, so one side of this angle is inside the polygon, one side is partially outside the polygon, and the side which is inside the polygon is larger than 180 degrees. So this means this is a reflex path. So this is how it looks like. And now we know how to solve this problem. So we know how to solve this problem with an O of n time. So given the polygon with n vertices, you can solve it in O of n time, which is a bit cheating. So I guess it's more honest to say that you can solve it in O of n log n time, because the linear time algorithm is somewhat complicated, very complicated. But you can solve this problem in linear time, in n log n time, or theoretically in linear time. And now we want to solve it in the bounded workspace model. Yes. So in the bounded workspace model, we're given this polygon. In constant workspace, this means that in read-only space, that means we have the sequence of the vertices along the boundary of the polygon stored in bounded workspace, and we have the coordinates of S and we have the coordinates of T. And what we want to do is we want to output the vertices of the shortest path. So these are also polygon vertices. We just want to have the indices or the names of these vertices. Yes? And so what I want to do is I want to see if I can just if I can just transfer the usual algorithm to the bounded workspace model. And so let me recall how the usual algorithm works. So the classic algorithm. And so the classic algorithm, it has several steps. So first, we triangulate P. So this is my polygon. So this is P. And in the first step, I compute the triangulation of P, like this. Here. Right? So it's a sequence of triangles like this, and you compute this, right? And what do we know about the triangulation of a polygon? For the triangulation of a polygon, the dual graph is a tree. Yes, so the dual graph is a tree. Is tree. Then the next thing is we find triangles for S and T. Delta S and delta T for S and T. Okay? So we triangulate the polygon, we find the triangle which contains S, we find the triangle which contains T. And in the next step, we find the path between S and T in this dual graph, right? So find path from delta S to delta T in dual graph. Yes? So we have this dual graph. The dual graph is a tree, and we find the path from the triangle which contains S to the triangle which contains T in the dual graph. And the last step is, so we propagate the shortest path along the tree path, using a funnel, something which is called a funnel. So in the last step, so I'm not talking about the details here, but so what you do is, so you have this dual graph, and in this dual graph you find this path of the triangles, so like this, and then there will be more triangles, this, from S to T. and you find the sequence of triangles, and then you walk along the sequence of triangles from S to T, and you maintain some structure which is called a funnel, and this structure will tell you how the shortest path looks like. So as you update it. And so now I want to put this algorithm make this algorithm a constant workspace algorithm. And so I can do all these things. So I have the polygon. I can, so the thing is I cannot do them one after the other, but I can somehow interleave them on demand. So I can find triangles for P. So I can find the triangulation of P, and I can have some efficient way of representing the triangulation of P in constant workspace. And I can, once I have this triangulation, I can also find the triangles for S and T efficiently. This I can also do. And now here, this is the crucial part. So we want to find, in the dual graph, we want to find the path from S to T. And here exactly we can use our algorithm for the shortest path in the trees. So that I described before. So here we can use our algorithm to find this path, to generate this path. But the only difference is now we don't have the tree stored explicitly as an adjacency list, but we somehow need to generate the neighbors. We need to generate the neighbors of a node in this dual tree on the fly, right? So whenever I said we look into the adjacency list to find the next neighbor or to know where we have to start, all of these things we need to do implicitly. So instead of just looking into the adjacency list, we have to call some procedure which finds this for us. But we can do this. And so all of this can be implemented. So we can, and in particular, so at the heart will be this. So that was the motivation why we wanted to solve this problem. And this gives us, so I'm not going to talk about the details because I don't have time, but so this gives us O of n cubed time and O of 1 space. Implementation of classic algorithm using the path in trees. Yes, so this is possible. But so this is maybe a bit too long. And so I think I will stop with this. So unfortunately, I didn't have time to get to the time-space trade-offs. But I will do this on Sunday. So on Sunday, I will start with time-space, space-time trade-offs. And let me just mention as the last thing, so this is O of n cubed time. So if you try to directly use what we did to find the shortest path in the polygon, this takes O of n cubed time. But actually, so if you start over and do something more directly, so more direct algorithm, so that's also possible. And actually, there are several algorithms. So I think we have 3 different. Or by now, I think there are 4 different algorithms for solving this problem. And so more directly, you can get O of n squared time and O of 1 space. So you can get this down to O of n squared by using something more direct. So this is what you get when you use the classic algorithm and try to directly modify it for the constant workspace model. Yeah, so that's it. So I think we're a bit late for lunch, but... so I'm done. So unless there are any more questions, but we can also talk before lunch, during lunch, after lunch, on the way to lunch, if you're busy. Yes? Okay. Thank you.